Good afternoon, everyone. I'm Denis Olyanin, a PhD student at Ternopil Ivan Palyuin National Technical University, and I'm happy to present the joint work my colleague, candidate of technical science Helena Zuprek, and I have done on transformer neural networks in Industry 4.0. Over the next few minutes, we'll see why self-attention models are rapidly becoming the analytical backbone of smart manufacturing. Our paper asks a simple question: how far can transformers push industrial intelligence? In answering it, we cover three critical application families: unstructured text, such as maintenance notes and system logs; computer vision quality control, where subtle surface defects must be caught in real time series sensor streams, the heartbeat of every Industry 4.0 line. In each domain, we evaluate performance, present case studies, and identify the practical constraints that still prevent wide adoption. Transformers were first introduced for language translation, but their power lies in three architectural choices. Self-attention weighs the relevance of every token or pixel or sensor reading to every other, capturing long-range dependencies lost in recurrent neural networks. Parallel processing means an entire sequence is handled at once, giving dramatic speedups over step-by-step models. Positional encodings preserve order so context isn't lost. From this foundation, several variants emerged: encoder-only BERT for understanding data, decoder-only GPT for generation, and the vision transformer, or in short VIT, when images are broken into patch sequences. The same mechanism that translates sentences can therefore flag faint scratches on leather or correlate temperature spikes with vibration drift. Industrial plants generate millions of log lines and freeform maintenance commands every day. Traditional regex parsers can't keep up, but transformers can. T4PDM, a stripped down transformer without usual encoder-decoder stack, predicts rotating machinery failures with 98% accuracy. In benchmark studies, LogBERT pushes precision, recall, and F1 score about 0.9 when separated normally from faulty sequences. A NVIDIA prototype that analyzes DGX server logs locates the root cause log lines with 99.9% accuracy, so an engineer needs only a few seconds to review the highlighted information. Finally, RoBERT CRF pipeline extracts equipment fault causes and remedies from Chinese reports at 0.95 F1 score, a leap over earlier RNN baselines. Factories use cameras to inspect each product, yet detecting a minute crack in a low-resolution image remains difficult. The Vision Transformers, or VITs for short, offers a solution to this problem. On laser sheet inspection, modern VIT outperformed lightweight CNNs, or convolution neural networks, in classifying defective versus normal samples, even with small, lower resolution datasets. Self-attention lets the network look at the entire image context, so it both flags and localizes the exact pixel region of a wrinkle or scratch. Because VITs are pre-trained on massive image libraries, a plant engineer can fine-tune a model for new parts in hours with only a handful of examples. Similar gains appear in PCB crack checks and weld X-ray analysis, where VITs remains robust under changing lighting or camera angle. Modern factories are equipped with numerous IoT sensors that continuously transmit vibration, temperature, and pressure data at kilohertz frequencies. Such self-attention models are especially effective at identifying subtle early indicators of failure within these streams. Transformer adversarial models on multivariate IoT data induce false alarms while catching subtle anomalies others miss. Imagine an LSTM model um, with transformer encoder raised the accuracy of remaining useful life predictions on real-world equipment datasets, demonstrating that hybrid designs can leverage both local and global patterns. In a recent plant trial, a transformer-based framework lifted product yield from 78 to 89.6% while maintaining near real-time inference at the edge. These studies confirm that transformers are not just accurate, but deployable in latency-sensitive production settings. Transformers currently provide leading-edge performance across all primary 4.0 data streams, text, images, and sensor signals. They consistently exceed 90% precision, identify defect missed by convolutional neural networks, and predict equipment failures several days in advance. Nevertheless, three limitations remain: the quadratic memory requirements of the attention mechanism, the need of transparent reasoning that operators can trust, and the difficulty of deploying large models on low power edge devices. Ongoing work on sparse attention, model quantization, and visual saliency is addressing these issues. If these challenges are overcome, transformer-based AI is likely to become the central component of fully autonomous, self-optimizing factories. Thank you for listening.